Alright everyone, take a look at this ramp. Think of this not just as a piece of wood, but as the number line itself. Just tilt a little bit. Now imagine we're dropping a ball on this slope. See these holes? Each hole represents an integer, like -1, 0, 1, 2, and so on. Here's the trick. The floor function works exactly like gravity on this ramp. Let's say your number is 1.9. If you place a ball right there at 1.9, it's not going to just stay put, right? Because of the tilt, it's going to roll, but it can't roll up to 2. It has to roll downwards, to the left, until it falls into the first hole it hits. And which hole is that? It's 1. So that's why the floor of 1.9 is 1. It's always about the hole you fall into when you're pulled down to the nearest integer on your left. It's like the number is looking for a place to rest at the floor level. Now here's where it gets interesting. What happens with negative numbers? Let's say we're looking at -1.2. If you look at the ramp, -1.2 is sitting just to the left of -1. Now remember the rule. The ball always rolls to the left, toward the smaller numbers. So if you place the ball at -1.2, it's going to roll past -1 and slide all the way down into the -2 hole. See that? Even though it's physically closer to -1, gravity pulls it down to -2. That's why the floor of -1.2 is -2, not -1. It's always the integer to the left, no matter if you're in the positive or negative zone. So let's do a quick test. What about 2.2 and -1? For 2.2, the ball is just past 2, so it rolls back and lands right in the 2 hole. Easy, right? Now for -1, the ball is already sitting exactly on the hole, so it doesn't need to roll anywhere. It's already floored. The answer is just -1. Remember, if you're on a hole, you're home. Okay guys, let's walk through some examples involving floor function limits. Number 1, the limit of the floor of x minus 1 as x approaches 2. To do this, we need to look at it from both sides, the right and left limit. So we have the limit of the floor of x minus 1 as x approaches 2 from the right is equal. If x is slightly more than 2, let's say for example 2.1, the limit of 2.1 minus 1 as x approaches 2 from the right is equal 2.1 minus 1 is equal 1.1. The limit of the floor of 1.1 as x approaches 2 from the right is equal, the floor of 1.1 is equal 1, so the final answer is 1. Okay? And the limit of the floor of x minus 1 as x approaches 2 from the left is equal, if x is slightly less than 2, means for example 1.9. So we have the limit of the floor of 1.9 minus 1 as x approaches 2 from the left is equal 1.9 minus 1 is equal 0.9, and the floor of 0.9 is equal 0. So we have 0. So since the limit from the right is 1, is not equal to the limit from the left, so we say that the limit does not exist at x is equal to. Okay? Number 2, the limit of the floor of x minus 1 as x approaches 2. First left hand limit, the limit of the floor of x minus 1 as x approaches 2 from the left is equal, if x is slightly less than 2, for example 1.9, so we have the limit of the floor of 1.9 minus 1 as x approaches 2 from the left is equal, the floor of 1.9 is equal 1, so 1 minus 1 is equal 0, and the limit of the floor x minus 1 as x approaches 2 from the right is equal, if x is slightly more than 2, for example 2.1, so the floor of 2.1 is equal 2, so 2 minus 1 is equal 1. Since the limit from the right is 1 is not equal to the limit from the left, we say that the limit does not exist at x is equal to. Number 3. The limit of x plus 1 times the floor of 1 over x plus 1 as x approaches 1 from the left. If x is slightly less than 1, for example 0.9, and if we plug in 0.9 for x for the floor function, we have the limit of x plus 1 times the floor of 0.9 plus 1 as x approaches 1 from the left. 0.9 plus 1 is equal 1.9, and 1 over 1.9 is the number between 0 and 1, means 1 over 1.9 is between 0 and 1. Okay, so the floor of 1 over 1.9 is equal 0. Okay, so here is 0, and 1 plus 1 is equal 2, so 2 times 0 is equal 0.